let's start the 5-4 theory, the second part. I think we only have 3 classes remaining, including today's. So today I will finish the 5-4 theory, and then basically we are trying to consider the less than 4 case, and then next week we will do the relativistic fermion (RG), and then the remaining one we will discuss the CFT, and then we will have the term paper. And then if people are interested in learning more about CFT, then if people are more interested in learning about CFT, then I can give 2 more lectures if people are interested in. But maybe we don't need to do that. Okay. So review the 5-4 theory. Basically, we start with a RG flow where we basically have quadratic term, this one, right? Plus the interacting term, like this one, right? And then we have this kind of flow diagram. So this is the R0, this is the mu0. Basically, there's a Gaussian fixed point, and then we have this kind of flow equation for d greater than 4, right? And then we basically see this before. So for the massive term R0, it's keep growing, and then the interacting term basically is the irrelevant term, basically goes to 0 in here. Okay, but something very interesting is, if let's start with some parts which R0 is vanishing. Suppose we start at this point, right, where this point R0 is 0, but U0 is not 0 basically. But you still know it will keep generate R0, and then since R0 is relevant, so it will flow away from the fixed point. It's not flow into the fixed point. So this is something very interesting. Even you start at a theory which has a 0 mass, but you can still generate mass term from the RG analysis. Okay. So basically, this is what we learn last time. I don't know why the share screen has okay, I see. Anyway. Okay, so that is what we learned last time. Now we want to discuss about the critical point, near the critical point. The critical point, right? So the idea of phase transition basically is understand the divergence of some properties near the critical point. And then that can be characterized by so-called the critical exponent. Near the critical can compute the critical exponent. So basically, it's characterized the phase transition behavior. So we have learned what kind of critical exponents. One is the mu, which corresponds to the divergence of the correlation length near the critical point. So it's a power law divergence, right? So remember, T is near the critical point. So it's a transition temperature, TC. It's near the TC. It's a way to characterize how the correlation length divergence, right? So this is one of the critical exponents, mu. And then the other one is also we have discussed. It can be extracted from the 2-point function, the Green's function, which as you know, there's additional eta term here. So this is evaluated at t equals to 0, which is at Tc, where it's divergent. So eta is another critical exponent. There are many critical exponents, which there is some relation, and then it also corresponds to some to the physical observable. So there are the critical exponent. So, and then it's basically tells you what kind of even different kind of critical system they have. If they have the same critical exponent, they will belong to the same universality class, meaning they behave similar. How they divergent, or what the form of the divergence basically are identical. Okay, so the other critical exponents can be obtained by, for example, measuring the heat capacity, the CV, which also has a divergent near the critical point. So it's characterized by the alpha. Also the susceptibility, chi, which basically is the magnetization divided by the external field H, which is the definition of the susceptibility. Also has divergent, which is the critical exponent is called a gamma, and also the magnetization. You can measure the magnetization. Also has a divergence near the critical point. Okay. So below, basically, it has a magnetization for IC model, right? Has a magnet. Below TC, there's a magnetization. So this is when it's approached. And then, of course, we can study how the magnetization diverges at finite edge, the external magnetic field. So also have this kind of divergence. So this is another critical exponent. So we have this alpha, beta, gamma, mu, delta, and eta exponents, which gives you which is a way to characterize the universality class for phase transition. Okay, and this kind of phase transition basically is a way to can be understood from the singularity in the free energy, okay, or the free energy density. So singularity arise from the singularity of free energy density F, which by definition is minus log of your partition function divided by the volume. Okay. So as you know, this free energy density is a function of T, right, which it has a TC in here, external field H, and then some interaction term I label by mu naught. Okay, and then recall this, what is this T for? So if you remember the fivefold theory, which in describing the phase transition, you learn from the STEMAC. Basically, this you replace this by T minus TC. So this is just a reminder. When T less than TC, there's a spontaneous symmetry breaking, right? So you basically corresponds to have this kind of potential well. Then you're locating the ground state as a finite magnetization greater than Tc, which corresponds to T greater than 0. Basically corresponds to this is equals to 0, and then you're back to a symmetric case, right? You don't have any magnetization. So we can identify this T just like the R naught in our fivefold theory or in our RG analysis. So the purpose now is we're trying to study the divergence or the singularities of the free energy from the RG point of view. where we did some analyzed before. Okay, so we'll put in the question from RG analysis, right? We should know how does the density, free energy density behave under RG. So let me equate this F by doing the RG, because they are the same when you're doing the RG, right? You integrate out some of the part, but the total degrees of freedom or the total form is the same after you rescaling, okay? But as you know, you need to rescale. So this comes from the rescaling. So the volume basically got rescaled by D minus D, S minus D. And then this is the free energy density. And your coupling parameter becomes like this one before. So this part is from the RG flow. We know how the coupling constant changes when we're doing the RG and the rescaling, right? So this is basically what we did before. Okay, so this is our starting point. So we can extract the critical exponent. So we're now using the RG to extract the critical exponent, and then want to compare the RG analysis with the mean field, and then see that do they agree with each other. Okay, that is the motivation. Okay, so this part is clear, right? Okay, so now we can compute the critical exponents from first the mechanization. So of course, mechanization can be directly obtained from the free energy density, which I like. So the mechanization, according to this picture right here, must comes from t less than 0. So I put the minus t here. H with external field, mu naught interacting term, which the mechanization comes from the partial derivative with respect of the free energy respect to the external field, which of course give you the mechanization. Evaluate at H equals to 0. Okay, as you know, so you can see from here, right? If we expand this free energy by Taylor expansion, the only non-vanishing term evaluate H equals to 0, it's the linear term, right? So you basically will put this here, and then the linear term is something like this one, right? Of course, there's higher order term, but when you put H equals to 0, it will be 0, so I don't need to evaluate that, right? That is basically cancel out, right? And then that's will give you the mechanization. After the RG process, you get this term, right? Okay, so this total will give you S1 minus D over 2, right? Basically scaling. And suppose, consider this is the order, this becomes like order 1. Okay, so then we can replace S by T, and then asking about how does its divergence. Okay, so it will become T modulo. So if you replace this by 1, and then you can replace S by T with this power 1/2, right? Because this is 2, so it's square root of 1 minus D over 2, okay? With this mechanization 1, 0. And this is BF T minus 4 over 2, okay? So clearly, if you compare this one, at near the critical point, which, as we discussed before, has this kind of beta divergence. So we can extract the beta in here, which will be nothing but D minus 2 over 4. So this is from our RG analysis, we get the critical exponent from the mechanization beta. Okay. Of course, we can do the same thing for the susceptibility, chi, which is evaluated, of course, at H equals 0. So susceptibility, meaning the mechanization divided by derivative with respect to external field H. Okay, evaluate at h equals to 0. So this part is clear. So you know that indicates you need to do twice derivative with respect to h for your Green's function. So it will give you minus d times 2 times 1 plus d minus 4. So basically this times 2 put in here, right? So in total, you'll get s2, s squared, chi t squared, 0, u naught s4 minus d. And as said before, you try to think this is evaluated around order of 1. You replace s squared by t, so it gets basically t in minus 1, right? So this is basically what you get. Okay, and then as you know, the divergence characterized by gamma here. So you now get the critical exponents from the susceptibility gamma equals to 1 here. Okay, and then the third one you can get is the heat capacity, right? The specific heat basically is the second derivative with respect to the temperature or your free energy density. So as you know, the free energy here, so you need to do twice derivative of this term, right? So it will give you s to the power 4 here. So we will get s4 minus d in the free energy here, right? And then this is just the heat capacity s squared. So we just put everything back in here as usual. Mu naught s4 minus d. And then the same before, you consider this is some kind of order 1 value, and then you replace s by t, and then see how it's divergence. So it gets basically t to the minus alpha, which alpha will be 2 minus d. So as you know, if t is equal, s is equals to t square root, and then you replace here, and then you basically get this value, right? So this is your another critical exponent, alpha. Okay. So these are clear. You have alpha, beta, gamma evaluate, and then also the magnetization, n, which you want to know how its divergence at the external field h equals to 0. Oh, sorry. So this is evaluate. So we have this one is evaluate at h equals to 0. The other one is you want to evaluate the magnetization near the critical point. So it's basically near t equals to 0 with finite external field. So as you know, magnetization is derivative of this. Evaluate this one, right? So this is said before. So but since you want to so this is the same, right? You want to derivative with respect to h. And then if you look at the free energy, h has this coefficient. So you need to pull this out in here, right? So it's the same will give you s1 minus d over 2 magnetization 0 h. So I just write what I have before. Sorry, this is s4 minus d, okay? And then you try to make this is the older one parameter, and then you can replace this s by h, same as before. So you get this one, 0, 1, h, d minus 4, is 1 half d. And then you evaluate at t, at h equals to 0. So basically this is 0, okay? And then you know the critical exponent for magnetization is h1 delta, okay? So it's directly get delta equals to d plus 2 divided by d plus 2. Okay, so now we basically extract all the critical exponents from the RG analysis, and then let's just pull out the table. So this is some kind of mean field, which is the Landau 5-fold theory that you learned in the in your stomach, and then this is the Gaussian fixed point RG fixed point. RG analysis at d greater than 4. So we can compare all the critical exponents, alpha, beta, gamma, delta, mu, and nu. So this is what you learn in your stomach. There's a jump, right? This is 1/2. I just pull out the number here. That is what you learn from stomach, right? Okay, now from what we did in the RG analysis, we have d minus 4 minus d divided by 2. So I just write down what we derived before, right? So this is just what I wrote down. So we clearly see this one is the same, this one is the same, this one is the same, right? And then maybe we can check if we put d equals to 4, basically this is 0. D equals to 4, basically this is 1/2. D equals to 4, basically this is 3, right? So at d equals to 4, basically it fits quite well, right? The RG analysis, right? So that's what we learn, but doesn't agree at d greater than 4. That's what our observation, right? So what does that mean? Meaning the mean field may be incorrect, or the RG analysis is incorrect. Okay. The answer is mean field is correct. Correct. At d greater than 4, but not the RG analysis, because we are doing things perturbatively, and then okay. So the quick answer is mean field is correct. But why? Why the RG analysis didn't give us the correct answer? Why? Let me be precise. Why RG analysis doesn't agree with mean field? Agree with mean field if mean field is correct. Okay, so we need to be very careful about the divergence of function, because as we discussed before, all the divergence we discussed, for example, the chi, the mechanization m, we only consider the divergence start from this prefactor s, for example, right? We only discuss how the divergence for this prefactor, but we don't discuss any divergence behavior for this mechanization. They can also contribute to the divergence. So you need to consider. So the answer, for example, mechanization evaluates at this can also cause divergence. Also has divergence. Okay, behavior, divergence behavior. You need to consider. That is the answer. So now we can see how does this correct our RG analysis. So let's start with the mechanization M. So we did this before, right? We're saying it's divergence with this prefactor. That's what we discussed before. And then we have this one. And then we're saying this is just some kind of regular function. So we only care about divergence and get the critical exponent, which is incorrect. If we treat this properly, according to Landau, This mechanization also has a divergence form, behave this like this one. So this is from the Landau analysis from the 5-O theory, right? Mechanization has this kind of form, right? Okay, so you need to put this back in here as a whole. So as a result, you need to replace in just times this one first, and this you need to replace the r by 1, right? And then mu is with this with this, so you need to replace this part and this part in here, right? In here, okay. So you need to take square root of, so r is 1, mu is mu naught t, d minus 4 over 2. So you need to combine this part and this part together. As a result, you get this kind of correction, which is the same as Landau's here. The same as Landau's, right? So this is something remarkable, that Landau is correct, mean field is correct. And then if you treat your function correctly, the divergence correctly, you get the result, okay? We can also check the other one, which also is from the mechanization, and then want to know the delta, right? As we know, this has this form, mu naught hd minus 4 divided by 1 plus 1 half d. Okay, so this is basically, and then Landau tell you the form of, sorry, Landau tell you this has the form like h divided by mu, like 1/3, so 1/3. Okay, so you can replace this by this value here, here. So you get h. So I just write this down again. The plus 2, and then this replaced by, so h replaced by this one, right? And then mu is basically, so u replaced by this, h replaced by this. So I only have minus 1/3 here, right? And then h minus 1/3 times this coefficient, d minus 4, 1 plus 1 half d. Okay, basically this is the form. And then you can basically massage the h function here, and then you get mu naught 1/3. I'm writing anyway. I don't know is it necessary to do this, but let me times 3 in here. So it will be 3d plus 2, right? So if I times 3, this is 3d minus 6. And this is I times 2 here, right? Would be minus 2d plus 4, something, plus 8, right? So I'm trying to recombine this and this. Okay. And this is nothing but 1, I think. Sorry, 1/3. Okay. So this is d d plus 2. So d plus 2 divided by 3 times d plus 2 will be 1/3. So as a result, this will be 1/3. Okay. So basically, sorry, it's here. So that's it. Inverse. Because this behave like this one. Okay. So basically agree with the mean field of the lambda. Okay. So now we know that. But why this happened? Because divergence of mu naught times this. We know the interacting terms goes to 0, right? At t equals to 0, right? But the corresponding, even though the interaction doesn't, what I want to say is the interaction is somehow irrelevant, right? But the mechanization, according to Landau's analysis, depends on this term, right? So it has a very dangerous divergence in the mechanization. So when mu naught interaction goes to 0, you realize the mechanization has a divergence, right? So we somehow called mu is a dangerous, irrelevant variable because it can cause divergence of your mechanization, some observables in here. And this observable will give another additional divergence in the when you do this RG analysis, right? So that's if you take this into account, you'll recover the Landau's result. Okay, so that's we need to keep in mind. And then there's other important consequences why mean field is correct, right? There's another thing we want to discuss because as we know, mean field doesn't really take care of the quantum fluctuation, right? But the RG analysis we did, we do have this kind of quantum correction. So suppose the quantum correction should give you a better result compared to mean field. But according to what we discussed here, mean field seems has a better result compared to the RG analysis. Okay. So
老师问一下哦，
好
mean field 没有考虑 fluctuation 吗？可是 mean field 的时候不是有什么一个平均值再加上一些什么东西吗？这样算有考虑 fluctuation 吗？
哦，如果有加就有，没有加就没有。
啊？
有加就有，没有加就没有。平均
可是不是都会加？我们不是都假设说什么是就是我们的物理量是一个什么平均，然后再加上一个什么小小 fluctuation， 然后弄进去之后，然后把二次项丢掉这样子。
那二次项丢掉就是没加。
哦，二次项丢掉这样就不算 fluctuation， 就没有 fluctuation 哦。
通常我们是说，譬如说 large n treatment 下的 saddle point 就是 mean field，然后 on top 有一些 correction， 这就是 quantum fluctuation 的 correction term。
等等，老师说什么 large 什么 saddle point 可以再说一次，我刚没听清楚。
就是说你在做一些强关联的问题，你要怎么把高次项丢掉或不丢掉？它取决于高次项，就是说，譬如说高次项的系数是多大多小，对吧？那个 large n treatment 是一个可以用 n 去控制你那个高阶项的多大多小。
哦，
所以如果单纯 mean field 就是把我所有的高阶项都丢掉，然后我们可以在 mean field 上面再考虑高阶项会对于你的可观测量有什么影响。那我们这个就是 perturbative 的一些做法嘛，然后这就是 large n 的一些做法，或者是 1 over n 的做法。
哦，好，谢谢。
所以你一开始讲的比较像是说，你一开始就起手在考虑 large n 下 quantum fluctuation 在 mean field 下的一些额外的作用。
哦 ，OK， 好，了解。
如果你不考虑那些额外的作用 ，mean field 是没有 quantum fluctuation 的，就是这样。
好。
Okay, so mean field is since mean field doesn't consider quantum fluctuation. So we will think mean field should not get correct result. However, singularity is the key point to extract the singularity is the key point, is the key to extract the critical exponent, right? Critical exponent. So if we only, so the idea is if we only consider the quantum correction, on top, correction on top of the mean field, singularities should not be changed because it's just a correction unless you sum over all the correction, infinite terms of correction. It can cause singularity. Just several terms of correction doesn't change the singularity. So it will. So basically, unless you can do infinite terms of the quantum fluctuation, otherwise the singularity will not change. Okay. So the idea is mean field is correct, in the sense that unless you can, or I should not say it is correct. I should say that the RG analysis will agree with the mean field because the RG analysis we did it is perturbatively. It didn't consider infinite term of the quantum correction, so it cannot modify the singularity. So it must agree with the mean field. Okay, that is the statement by the singularity. So I should Y mean field, or I should state Y RG agree with mean field. The reason is just a correction doesn't change the singularity. Okay, that's what we need to state. Okay. The other part we want to know is for d less than 4. Now we know mu naught is relevant operator, right? Relevant variable, observed variable, quantum correction or quantum fluctuation cannot be treated perturbatively, right? Meaning that it can modify your mean field result, can get different critical exponent. Okay, so that's what we will expect. So if we do the same thing for d less than 4, then we should not expect to get the same critical exponent as we get in the as we get from the mean field, and that will be the statement we should see. So, but to get to that point, we need to understand how do we do the RG for d less than 4. Okay. So now we need to, so that's give us a very strong motivation to study d less than 4 RG analysis for bifold theory. And then the question is, since it is a perturbative RG, we need to find the way to control the divergence, or we need to find a small parameter to do this perturbative RG. So the difficulty is we need to find a small parameter. A parameter for perturbation. But there's a trick called Epsilon Expansion. Okay, so this is the idea. Okay, now we want to do this kind of Epsilon expansion. So what is Epsilon expansion? The idea is we want to define epsilon, which is equals to 4 minus d. So we consider epsilon is a small parameter, which corresponds to the dimension very near to the 4, and then use it as a parameter to do RG. This is the idea. Okay. So to do this, we need to recall the beta function. So from the RG analysis before, we know for the R, the quadratic term, basically define this one. We get this kind of beta function. So as you know, this indicate interaction can generate R0 term, right? And then we also have this kind of interacting beta function parameter, which will be 4 minus d, which, as we know, when d greater than 4, the interaction is irrelevant, but d less than 4, it will be relevant, and it will become larger and larger. So at this point, for d greater than 4, the picture should be something like this one, right? So this is the U naught, R naught. So let's start with the Gaussian fixed point. It will goes out, so it will flow away, right? So we want to ask, is there another fixed point? Right. So if there exists a fixed point, you must add in some terms to make this becomes 0, right? Right. That is the way to have a fixed point. So you need to stop. So it's to stop the growth of mu naught, right? So you need to have additional term, right? And then this additional term must becomes some kind of negative coefficient, and then in terms of mu naught square to stop its growth. Okay. So you need to consider some kind of second order perturbation. And then that's what we learned before. We discussed before about this interacting term. We need to consider the interacting term squared, right? And to treat it properly, that is done by Wilson and Fisher. They invent called the small epsilon expansion, which consider as a parameter. It's a small parameter to control this RG, to control the RG analysis. Okay, that is the idea. Okay, so it's called epsilon expansion. Okay, so if we have this small variable a epsilon, and then do the analysis, and then we just take epsilon. So if the RG, and after the RG analysis is done, we take epsilon to be 1, which corresponds to the three-dimensional case. Okay, that is the way that people can analyze the three-dimensional behavior, the critical behavior of the system. Okay? And this is our approach. Okay, so as this approach, then we just write down the beta function again, which is nothing but this term, right? 1 plus r naught. And then the beta function for the interacting term, which we know we must have some kind of second order with negative sign. Sorry, this is not to control it. Okay, so this is what we need to put back from perturbative RG analysis. So which this term comes from the partition function analysis, or the self the effective action. So the effective action basically, which is derived from integrating out the fast mode for the FIFO theory, which, as we discussed before, which contains the non-interacting part, the interacting part, which integrates out the fast mode. So it's basically the expectation value. So basically this point gives rise to this and this, right? And then of course the second order term is that this part must comes from the second order term of the effective action, which we discussed before. This is the interaction square take expectation value minus the interaction expectation value square. Okay, so this is the term which can give rise, to the another quadratic correction. Okay, so how do we compute this one? This is nothing but 8 field in the integral, right? So as you know, the integration square must be u square, and then I must integrate out 4 fast mode. So must contain this kind of integration times the rest of parts, right? Sorry. Okay, so this expectation value, which gives you the 4 fermion interaction term, have to integrate out the best mode, right? So that is what you need to evaluate. Okay. And then this we can use the Feynman diagram to simplify our calculation. So can be computed from Feynman diagram. Okay, so there, what are the corresponding Feynman diagrams? So as you know, we need to have 4 branches for the slow mode. So the idea is we can just put 4 slow mode, 2 in, 2 out first, right? It must come to be slow mode according to the Feynman diagram, right? And then we need to consider the integrate out 4 fast mode. So we just connect these two together, and then it's a 4 fermion interaction. So this must be the fast mode, right? And then must connect this one because there's no other branches. So this is one possible Feynman diagram, and this corresponds to interaction vertex u0. Okay, so this is one possible Feynman diagram, right? The other one basically is just exchange the momentum k and k plane, right? You can exchange them. So the corresponding is also 2 in, but the 2 out, one is from here, the others from here, right? And then same as before, this is the fast mode, and then basically this is the way you can draw it. And then there's a third one, which also 2 in, 2 out, right? But you draw it in a different way, where the fast mode is connected vertically. So 2 in, 2 out. So this is the fast mode. This is slow, 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 slow. And the other possibility is also 2 in, 2 out, right? However, you don't need to connect the figure. It can be connect by its own branches. So you can something like this one, 2 in, and then this is the disconnected patch. Right? So in, out. Okay, basically. So you have this kind of 4 kind of Feynman diagram corresponds to the square of the interaction term. So just a quick recap. The interaction terms, the square of the interaction term after integrated out the fast mode contains 4 branches of the slow mode, and then the corresponding Feynman diagram is shown here. So we basically have one disconnected Feynman diagram, and then and then the other 3 kinetic diagram. And then you see these 2 are the same, just exchange the outcoming slow mode. And C part is a little bit different because you notice the arrow you can draw is only satisfy the 2 outgoing fast modes according to the lower vortex. And then according to the top vortex, it's a fast mode must be ingoing mode. In here, you can switch the direction of your fast mode. So it can be either incoming or outgoing. Okay, so let's back to the class. So as we discussed, we are trying to compute the second order term. Basically, we need to compute this 4 Feynman diagram. So let's discuss A first. So this Feynman diagram corresponds to this picture, right? So this is the slow, slow, fast, slow, slow, right? Fast. And then we can label by K1, K2, K, and then as you know, the momentum is conserving. So this is, if this is K3, this must be K1 plus K minus K3, right? And this is K4, right? And then as you know, we can treat this with another figure, which we just reverse the error, where this is become in and this one is in and this is out. So we can have this kind of 2 Feynman diagram together, considered together, right? And this just nothing but doing the integration. So we keep the slow mode. This is the slow mode. So this is the 4 slow mode. We put so the outcoming is K4, K3, and the ingoing is K1 and K2. K2 and K1. So this is the slow mode that we don't integrate out. And then this is the fast mode. We integrate it out, right? So the fast mode is only these 2, right? So so this will be K1 plus K minus K3, which corresponds to this outgoing part. Okay, and then the ingoing part for the other one is K1 plus K minus K3 as well, corresponds to this both vertex, right? And then also this is the outgoing vertex, which is K. And this is the ingoing vertex, which is K. And basically we need to integrate out, and then we put the momentum conservation. K1 plus K2 equals, sorry, K1 plus K2 equals to K3 plus K4. So this is the delta function. And of course, this is the order of mu naught squared. So that's basically the Feynman integral. We need to integrate out this term here. Right. Okay. And then now let's consider the B part. B part is similar as A part by exchange K3 and K4, right? Because you know this, just exchange this part, right? This part and this part. So just exchange K3 and K4. Okay. Now C part, as we know, this contains this kind of diagram. And then, as you know, this fast mode only has one direction because 2 in must has 2 out. You cannot has this kind of 2 in 4 in state. So the red part is forbidden. So only has one term. Okay. And then the B part is the disconnected graph, right? So this is the disconnected graph, right? Which, if you write down the form in terms of expectation value, so it's disconnect. So and each one corresponds to the expectation value of the interacting term. So this, since it's disconnect, you just take this square, right? Okay, basically. So now, sorry. So what we know is the next order direction term is the interacting square expectation minus the expectation value square, right? So since this term is equals to expectation value square, which contains in here, so basically this term will automatically cancel out this term. So as a result, we don't need to consider this term because it will cancel out the parts we already compute, and then we take that square, right? So now we only, or we should, or just equivalently, we can say this part will corresponds to 1/2 of A Feynman diagram plus B Feynman diagram plus C Feynman diagram. Because the D part will cancel out with the expectation value square, right? And then, as we know, this one has 2 different kind of configuration, which corresponds to this one, right? Plus 2 in, 2 out, and then reversely, right? So this has 2 terms, and A is similar to B, so also has this 2 terms, and C only has 1 term. That's 1 term. And then each term, each Feynman diagram will give you the same amplitude, so it will equivalent to 5/2 times the thing we want to compute here. So that is what we can directly get from the result. Okay, so this is something we need to compute. So this is nothing but this part. Let me this part. So we need to times 5/2. So this is the thing we need to compute, okay? So this is still not easy to compute, so we need to do some kind of assumption to make the things easier for us, because we just want to get some qualitative results. So let's do some approximation. So the zeros order approximation is assuming the slow mode is extremely slow, such that the corresponding k basically goes to 0, right? So that corresponds to some kind of Feynman diagram, only consider the momentum for the fast mode, because the slow mode doesn't contain any momenta, right? So this is a very, very rough estimation. But let's suppose we start from here, which can make our life easier, because we only need to integrate out the momentum, which is the same momentum, right? So if you really want to do rigorous calculation, this is not easy, because you need to integrate out the k here, right? But the fast field also contains the other slow mode momenta, which you don't know how to do it. But if you consider K1, K2, K1 and K3 are 0, which is basically you use the same K label here. The calculation is relatively easy, and it will correspond to making the slow mode is extremely slow. Okay. So suppose this is the assumption we want to do, and then integrate out the fast mode, which basically take fast. So we are doing this kind of stuff, right? Basically, that indicates you can integrate out the entire momenta, right? So this is nothing but with the same case. So as you know, this gives you one 2-point function form, and this gives you the other 2-point function form. So you get this kind of r naught square and then the square, right? And then this is basically the integral you want to do. And then so suppose in a spherical symmetric case, which is in our case, we can replace this d-dimensional integral into this kind of surface integral, and then define this part. Sorry, this is d minus 1. And then define this part as a, okay? So this is nothing but a, and then this just become a small integral you can do, which you can just replace k by lambda. So it will be lambda d minus 1, lambda square plus r naught square dl. Okay, and then we take lambda into 1 as we did for our analysis. So this is the zeroth order term we can get. Okay, so now that we want to know the interaction coefficients after the RG analysis for the rescaling. So before we have this kind of form for our beta RG analysis, as you would discuss before, right? And then the other one is the second order perturbation, right? Where the scaling, so this comes from the rescaling of the field, right? Which I think it becomes as divided 1 minus d divided by 4. Is 4. Yeah, scaling, right? And then you need to times the interaction term here back, right? Okay. Now, this term is what we compute in here. This is basically what I characterize the second order correction. Okay. And then recall the rescaling S is defined as this one, which we know which we know this will give you 1 plus 4 minus d dl. So that's the reason if we replace 4 minus d by epsilon, we have a small parameter for doing perturbation. Okay, so this is called epsilon expansion here. Okay, so now we can collect all the term, the original one we did, and then the second, the next order interaction correction, the one correction we did. So as a result, combine all these terms, we have this one plus, so the prefactor is the same as 4 minus d, which we expanded, assuming 4 minus d is a small number parameter. We have 1 plus epsilon times dl times the first term is u naught, and then the second term has a minus 5 over 2, as we discussed before. This 5 over 2 comes from this part, right? And then this is the minus of this one, so we get a minus. So this is the minus 5 over 2 times the term, which is u naught square, times a divided by 1 plus r naught square. Sorry, 1 r naught square, so square. Square. Okay, so basically this is the thing we have. Okay, so this is nothing. We can expand order by order in terms of L. We get u naught plus epsilon mu naught minus 5 half u naught square a divided by 1 plus r naught square times the L, and then the order of the L square. Okay, which directly give us the beta function, which d mu naught dl will equals to epsilon mu minus, so basically this part, mu naught square a divided by 1 plus r naught square, right? And then this is nothing by definition. This is the beta function for mu. Okay. Of course, we can further, assuming r naught is small, and then we can expand it. So it will be something like this one, right? Plus the order of mu naught square r naught square. Okay, basically. So this will be the correction we want to know that give you a new fixed point, which is called the Wilson fixed point. So as a result, we can get a new fixed point, which is called the Wilson-Fisher fixed point. Okay, which we can solve by taking the beta mu, sorry, I use u, beta u goes to 0, which we just equate epsilon u naught minus 5 over u naught square a u naught star square, right? So this is the beta, the fixed point. So we immediately solve this fixed point is 2 epsilon minus 5a. And then we also need to know the r naught square, right? So how do we obtain the r naught square? also from the beta function. So this is beta r, which we know this is 2r naught plus mu naught a divided by 1 plus r naught. So we put this star, star, star. So we can just put this u naught in here and then solve the r naught. So the r naught is something. So we can expand this one. So we're trying to expand this 1 minus r naught squared. So it will somehow approximate to epsilon over 5. Okay. If you set this equals to 0. Okay. So now the RG flow in the parameter space for d less than 4 will behave like this one, where this is your R naught and this is U naught. And as you know, now the beta function for R is the same, but this Gaussian fixed point, now the mu becomes relevant, so it will flow out, but to a new fixed point, which you solve as a U naught star, R naught star, right in here. So this is the new fixed point, and then the flow will behave like this one, and then this repel out. So this is the Wilson-Fisher fixed point. So now in this kind of d less than 4 dimension, you do have two fixed points. So one corresponds to the Gaussian fixed point. So I should use the other color. Gaussian fixed point and Wilson-Fisher fixed point, which corresponds to 0, 0. And this corresponds to 2 epsilon divided by 5a minus epsilon over 5. Okay. So since you know the fixed point, the new fixed point, then you want to study the flow near the Wilson-Fisher fixed point, like what we did for the Gaussian fixed point. So how do you study the flow? As we discussed, we're just trying to expand the parameter near the fixed point and then see how it goes away or goes into, right? So that's basically what you did for this analysis. So from this one, you can basically directly get the deviations of your parameter with respect to the RG expressed in terms of the beta function. So this will be the beta function for R, right? Because by definition, this part is the beta function. So you will have this kind of beta function behavior for R. Functional derivative of beta R with respect to two small deviation, right? So same for the delta mu naught, you also have the same thing, which will be the beta function for U, the same before. Okay, so you can use this to get the flow, and then this is nothing. You can return in terms of matrix form. So I will not replace this part, and this is nothing because the beta function, you know how it's a function with respect to R naught and U naught. So you can rewrite this as 2 minus 2 divided by 5 epsilon near the for the d less than 3 case. So basically, this is what we have, and then this is nothing but delta R naught, delta mu naught. Okay, so you can study this one, right? And then, of course, in this case, eigenvalues are this one. So eigenvalues which is also 2 minus 2 epsilon divided by 5, and then minus epsilon. And this corresponds to the eigenvector 1, 0. Okay. Now we want to study how the parameter changes. So as you know, the parameter in a generic form we said is k. So delta k is the changes of the parameter with respect to the RG process, which we use the DL, which give you. So we are basically writing this form, right? In terms of the this is the general form. For the above equation. So this one is nothing but what I write before. So if you want to, we can say this equals to 1. We just label R naught. R equals 2. So we basically just writing the previous explicit example in terms of a more general form, right? And then from this general form, you can study the flow just by consider. We write this as something like omega, right? Sorry, let's check. DL in here, delta k beta. And then this is nothing but the difference between the pre and post RG process, right? So, okay, so I'm trying to rewrite this is nothing but this one. So as a result, you know this is nothing but delta alpha beta plus omega alpha beta DL is. So this is the flow. You try to see how does the changes of the parameters after the RG step, and this will be the corresponding velocity, right? You want to solve as we discussed before. And then this is just an identity, and this is the eigenvalue you know. So as you know, for the eigenvalue, let's suppose the eigenvalue, which should use omega, eigenvalue is equals to this. The eigenvalue is equals to 2 minus 2 epsilon divided by 5, which corresponds to this part. Okay. We know the eigenvalue of t will be, since the previous one is just the identity, 1 plus 2 minus 2 epsilon divided by 5 times the L, which we can try to exponentiate. This one is nothing but s to the 2 minus 2 epsilon divided by 5, right? Because we call s, we said exponential dl, right? So we just can be expanded this one. So it will be s to the power 2 minus dl. Okay. So this give us a way to study the critical exponent, because recall the correlation length after the RG iteration will correspond to the S times the post RG iteration. So this is before RG, this is after RG. You get new covering parameter times the S, right? The scaling. So with scaling, okay. So this will behave, as you know, this is nothing but 2 minus 2 epsilon divided by 5 times R naught, as you did here before. So you are monitoring the first, the 1, 0 component, which basically corresponds to study how does the R goes, the parameter R naught, right? So the corresponding eigenvalue is here. So I just times this corresponding eigenvalues to get the new R naught here. Okay. So as you know, the idea is we suppose the one RG step, this will be the order of 1. Then we know how does the S behave as a function of R naught, and then we can extract the critical exponent, right? So it's nothing but 2 epsilon divided by 5 minus 2, 1. Okay. So as you know, by the definition of critical exponents is this one. So the critical exponent in this case basically is 1 divided by 2 minus 2 divided by 5 epsilon, which you can expand plus epsilon divided by 10, which if you put epsilon equals to 1.6, and then if you compare with the numerics results for d equals to 3, it's almost the same. Okay. Okay, so that is almost the same. Okay. Now comment. If we consider next order of epsilon square epsilon cubed, does it approach to the correct exponent? Okay, the answer is no, because we know if we don't do the answer is no, because it may not be a convergent series. Okay, that is the quick answer. Okay, now we want to consider d equals to 4. So we discussed the less than 4 case. So we want to consider, does this give you some kind of understanding for d equals to 4 cases, which corresponds to epsilon goes to 0 case? Okay. So so in this case, the beta function is just taking epsilon goes to 0 to get this kind of beta function. Okay, this is the beta function for d equals to 4. So remember, the first term has a d minus 4 mu naught, right? So when d equals to 4, the linear term basically vanishes. So you only have this quadratic term. And then now you can study the a. In this case, the coefficient you can compute exactly. So I just give you the number here. Okay. Now we can try to get study how does the coupling constant changes. Okay. So this is relatively easy because you know how to do this. This is nothing but doing the integration. Consider the length scale from 0 to L goes to L, which is nothing but this one, goes to minus BL, right? So I'm rewriting this B mu is nothing but define this one, right? So I just doing the integration right here directly. Okay, and this integration you know how to do it, because this is nothing but 1 minus mu naught L minus, because this is the square, so you know the upper bound minus lower bound, something like this one, right? So this gives you this one. This integral you know how to do, and then you just rewrite everything. So you know the coupling constant will be like this one. We'll do the integral. Okay. Okay. That is the form. So when you do the RG, basically you are changing the L. So you see at large L, the interaction term basically in the denominator, so goes to 0. Or if we write it explicitly, it will behave like BL term because this part will be dominant, right? And then it goes to 0. So as a result, the flow is similar as the d greater than 4 case, which you still have this kind of stuff, but the mu naught still is a irrelevant coupling, which goes into the Gaussian fixed point, right? So it's similar in terms of the flow diagram. Is similar as d greater, similar as d greater than 4. However, the how its approach to the Gaussian points is different than d greater than 4. Okay, then we can analyze it from the beta function. So how should we do it? So how it flows to Gaussian fixed point. It's different. Then d greater than 4. So recall at d greater than 4, the beta function is basically like this one, right? And then we can do the same trick before. This is nothing but integration like this one, right? Logarithmic function, right? So you basically get the form like this one, exponential L minus epsilon, which we can think this is S. So it's a power law. So it's power law approaches to the 0.
老师问一下哦，那个像图旁边写 GFP 是什么意思？
Gaussian fixed point.
哦。
Okay, power law. Okay, power law. However, for d equals to 4 case, we know this has this kind of form, right? 1 plus b mu 0 L, and then we're trying to put this back in here. 1 plus b log s. So it's logarithmically approaches to the fixed logarithmically, right? Approaches to a fixed point, right? So it's very different than the d greater than 4 case. Okay, it's flows slower, basically. Okay, now we will now the other question is, what is this line in d equals to 4 case? How do we obtain this line? Okay, this critical line. to obtain this critical line, we'll need to solve the equation. So, but this can be solved exactly. So this is the R function, the beta function of R, which we can use this to solve it, because as you know, the U naught we can replace by this one right here. So it will be A, sorry, U0 plus 1 plus B, U0 L. Okay, so now we can basically replace the dr by an integral. So this is nothing but the integral of this one, right? Because as you know, this is the difference. So difference will be 2 times the L. So we will put E2L in here. And then we need to do the integral in here, the L plum. And then we need to put this minus 2L plum, which basically can cancel this term out. And this is just the rest of the U part. So you are doing this kind of integral. Okay, that is what you need to integrate out. So it's of course this is not easy to integrate, but there's a trick to do it. Okay, so from the boundary condition, where we know when L goes to infinity, this must be 0, which flows to the Gaussian fixed point, right? So which means this L goes to infinity with plus, sorry what I'm writing. Okay, sorry. So basically I'm replacing this by 0. 0 will equals to this goes to infinity, which means this part must be 0, right? So it will be R0, 0 plus 0 infinity exponential. This one, this integral must be 0. 0 L plum. So this is what we can solve. So we can insert this with minus term in here to this equation, right? So this is the integral. So we can replace this. So we can replace this R naught 0 into this equation. So it will be R naught L will equals to exponential 2L. So the integral here from 0 to L will become L to infinity, because this has a minus sign. Okay, so we have a minus sign, L to infinity exponential minus 2L plum A mu naught 0 1 plus B mu naught 0 L plum the L plum. So we have this kind of expression to solve. Okay, so this has a term. This function has a term. Sorry, this function is not easy to do, but we can. We are approaching to the Gaussian fixed point, which we can somehow expand it this around L into infinity, which will be minus. So this is a large number. So this will be A divided by B if L goes to infinity. So basically need to do this just rewrite this in terms of L infinity exponential minus L plum. So mu naught and naught is basically, so L goes to infinity, we only need to consider this part, right? So this is the part we need to do integral. And this is called the incomplete Dharma function, incomplete Dharma function, which define incomplete gamma function A and X. So we start with X to infinity T. This is the definition minus T dt. So we can basically read out this function is nothing but gamma taking A equals to 0, right? And then taking T equals to 2L, right? And then this incomplete gamma function, you can check it from the Wikipedia, and then you can expand order by order. The leading order will be this by 2L plus 1, sorry, Okay, so if you replace everything back in here, you will get basically as L goes to the large number, so this will be the dominant per part, and then this 2L will cancel out this 2L. So you will basically get when L goes to infinity, R naught L will equals to minus A divided by 2BL, right? So this is basically the form you can get when L goes to infinity. And then, of course, for the U naught, L goes to infinity, U naught, and then we already know it will be this one. So we derive in here. Sorry, in here, right? Yes. So that gives us the critical line. But this is the line equation, where basically R naught divided by U naught is equals to minus A over 2, right? Because limit L goes to infinity. So that's basically the critical line you can get at D equals to 4. Okay. Okay, now we can get some ideas from D equals to 4 case. Okay. So first of all, the interacting part still goes to 0. So this is basically what you get. Goes to 0 at L goes to 0 limit, infinity limit, right? This is the form we get. So interaction is still irrelevant, but it has a different kind of velocity compared to the D greater than 4 case, because as we know, this is something like this one. Okay. So what I want to say is this is from the perturbative approach. The perturbative approach, right? So if we treat things perturbatively, although this will goes to 0, if we treat correctly, sum over all the terms, it will behave like this one. Okay, so that's indicate RG to the resummation to have this kind of form. So that is some kind of comment. Okay. Okay, so basically that's what I want to talk for the fivefold theory. Okay, so far so good. There's no questions at this point. So if not, I will spend maybe 20 minutes discussing the next stuff, which is the RG for the fermion case. Okay. Okay, so if no question, then we'll do the RG for relativistic fermion. And let's do it in 1D case first. Okay, so this can be followed in Shankar's book, chapter 15. Okay, so we already learned the 1D polarization, right? So we basically know how to treat interaction for this 1D fermion case. Okay, so from what we learned, we know the interaction is nothing. We can do this kind of forward scattering term, right? So this is basically the forward scattering term. Okay. And then also you have this kind of backward scattering term. And from this polarization, we know it can be mapped into free boson, and it is a massless free boson, which indicates it's gapless, right? So we basically learn that from the interacting fermion case, if it is a Ladinger liquid, or if we only consider the forward and backward scattering, interaction still does not open a gap in the spectrum. So it's still a gapless case, okay? So can we learn this kind of physics in terms of the RG point of view? That's basically the idea. So the idea is, can we understand the gapless phase in interacting fermion system in terms of RG. So what does this mean? That means we need to consider some kind of interaction. This interaction can gap the system, right? And in terms of the RG analysis, that means that this interaction couplings must be vanishes when we do RG analysis, which must be irrelevant. If it is true, then in terms of the RG language, the spectrum cannot be gapped if we approach the low energy theory. So there. So from RG point of view,
老师问一下哦，为什么是不是 gapless 这么重要啊？
因为它告诉你物质的性质啊。
哦，对对，会不会导电什么那个是不是？
对啊。
可是这个是因为有 interaction 的，所以又没有像说什么没有 interaction 那么具有这样，所以说是这样吗？
对啊。
哦，了解。因为我就觉得就是我有时候之前会觉得很奇怪，想说为什么有没有 gap 那么重要？哦，没事。
对。From RG point of view, the interaction or the coupling that opens the gap must be irrelevant, right? So the idea is, in terms of RG point of view, if the interaction that can cause the opening the gap becomes larger and larger, the system must be a gap system, right? When we goes to the low energy, where that corresponds to doing the RG. If it is the other way around, where the interaction that can open the gap becomes smaller and smaller, that indicates in the low energy sphere region, this interaction can be neglected, and the systems will remain gapless. So this is from the RG point of view, we can understand it. Okay. So this is what we should be able to learn from the RG, right? And then also in 1D, besides the bosonization, some of the case you can solve exactly. So the typical interaction we can consider is the Haber interaction. So let's consider in the lattice model, consider a fermion hopping from I to I plus 1. So it's the nearest neighbor hopping. And then we consider some kind of nearest neighbor Haber U, where we write something like this one. So we shift by 1/2. So this can be solved by Yang Zhenlin and CP Yang. So it's 2 Yang by beta ansatz. That at the chemical potential equals to half of the interaction strength, the modular of the interaction is less than 1, the system is gapless. Okay. So at this point, I want to emphasize that if we consider for this model, or this Haber model, if we start with some interaction mu naught, which is less than 1, and then we ask about the RG, if this mu naught keep growing and then it's still less than 1, then of course it's gapless. But if this is a relevant operator, relevant parameters couplings, then it will keep growing, right? So eventually it will become greater than 1. So at that point, it cannot be, it will be gap, because this model is exact solved by Yang, right? So it's already gapped. So from the RG point of view, if I start with this Haber model, this U, if I start with something less than 1, it must be less than 1 to saying the spinless fermionic system is gapless. So that is the idea. Okay. For knowing this, we need to study how to gap the system. So before understand or using RG to understand the gaplessness of 1D fermion. We need to know how to gap the system. Okay. So how to get the system? So we know there's two ways to get about the system. One is when we form a CDW order where we break the translation invariant due to the interaction. And this is happen when the interaction greater than 1. And second is we develop the superconducting order parameter, where of course we need attractive interaction, which corresponds to the nearest Hubbard model, U0 less than -1. Okay, so these two can get the system. Okay, but we need to understand, can this happen in terms of the some kind of simple tools which is the mean field approach. So this can be obtained from beta ansatz.
老师问一下哦，那负1到1之间的话呢？
负1到1之间的就是这个。
哦，对，对，忘记了。
就是 Yang said that if between -1 and 1 is gapless, greater than 1 is a CDW gap, less than -1 is a superconducting gap. But I will not talk about the beta ansatz because it's relatively advanced. But at some point we might want to teach if there's a condensed matter 3 course. Okay. But there's still some kind of simple way to understand this order, which can get the system. But so the method we can use is the mean field. Can obtain, so the idea is we can obtain this CDW and the superconducting orders from the beta ansatz. But the cheapest way is to use the mean field. Mean field can also obtain them. So mean field can also obtain the CDW and the superconducting order parameter. So how do we use the mean field to obtain this order? So it can be computed self-consistently. So we just shows you how to compute this self-consistently. So to define the order parameter, let's focus on the CDW first. The CDW meaning the charge density wave. So it corresponds to charge density wave order, which means there's a staggered order, which means when you compute the number operator at each side, it has a modulation, which modulates in terms of this one. So you have, for example, you have this size. So you have this kind of modulation in terms of the density. So it's a charge density wave. So it will break your original lattice symmetry, translation symmetry. Okay. So how do you solve this one? Is consider a mean field treatment by consider this we rewrite the Seidegger psi in terms of the original order with normal ordered two fermion operator. Okay. So if you redefine this one into your Hamiltonian, okay, so you just replace this into your Hamiltonian. So your Hamiltonian basically is this one, Hermitian conjugation, and then the interacting term, which will give you sum over I. So each one has this coefficient, and also this one. So the square will cancel this -1, but the cross term will be -1i. So that's basically the idea is the four fermion term you can replace by 2 fermion terms, because the normal ordered 4 fermion term is easy to get, right? Basically, this is 0 for ground state, right? Okay, so this is the mean field part. Okay. So the idea is the normal ordered. The normal ordered for 2 fermion terms in terms of ground state is 0. So you don't basically can drop out these terms. And this is the mean field Hamiltonian you are computing. Okay. So the mean field Hamiltonian is somehow non-interacting, which is quadratic in quadratic in fermion operator, fermions. Okay. So let's first write down my Hamiltonian in the momentum space, which I just do Fourier transform, right? And then my Hamiltonian can be diagonalized in the momentum space by replacing the inverse Fourier transform of your psi j into psi k. So it's nothing, but I think we did this before. It will diagonalize in the momentum space since it's quadratic. And then you also get this kind of term, cross term. So basically this comes from this part. And then you sum over OK, which give you L here. And the cross term is minus delta mu, sum over J. So recall there's a additional -1 here. And this will be times 1 over L exponential I L minus L prime J psi delta K prime psi K. Okay, so this is the corresponds to the Fourier transform for this component. Okay. So if you look at these terms, if you sum over this term, so you see there's additional -1j, which directly give you this kind of shift by k kind of Fourier component in here, right? Because this corresponds to pi when this is -1, so exponential I pi. So you can basically absorb into the k and get this form here. Okay. So now the idea is the Fourier in the momentum space. We know the spectrum. Sorry. For the for u naught equals to 0, it's a minus cosine function, goes from 0 to 2 pi, right? Since you can shift this k back, you also have this k plus pi part. Basically, you can rewrite everything in terms of the region from 0 to pi, because this will go in from when you goes from 0 to pi, and k plus pi will goes from the the other region, pi to 2 pi, okay? So you can focus on the interval between 0 and pi, and then rewrite your Hamiltonian in this form. So the integral become, so I'm rewriting my summation over k in terms of the integral. And then, as you know, since I only consider the half branch here, so this one only consider half of it, right? If I only consider k and k, so I must consider the other one, which is k plus pi. So this, when this, in this interval, this part belongs to 0 and pi, this part will correspond to pi to 2 pi of the original theory, right? So that's the reason I say I can only focus in this interval here and rewrite my Hamiltonian. So the first term still cosine k. So this is the diagonal part, right? As you write down. So the diagonal part will correspond to this one. So I just split this one into 0 and pi to 2 pi, and then I rewrite this in terms of this form. The integration will be 0 to pi, diagonal part. Okay. The off diagonal part will contain this term, right? Times this one. So this will be the off diagonal part here. Okay, and then plus the constant term, which is this part, right? Okay, so this is the Hamiltonian in the mean field treatment, right? And then rewritten in the half of the Briand zone. Okay, so this one, you can solve the spectrum because you know it's quadratic. You basically just need to diagonalize this matrix. So the energy is nothing but 1/2. So it's constant term. I just write it down, right? So this is just constant term, and then plus minus this eigenvalue here. This eigenvalue corresponds to integration over all the momenta defined from 0 to 2 pi, 0 to pi, sorry. And then this is nothing. The spectrum is plus minus cosine square plus delta square mu naught square, right? So this is nothing but this one. So this is corresponding energy you have. And this is times L. Okay. So I can remove this L and put everything here, right? So the ground state corresponds to the minus sign. The ground state corresponds to field order minus sign. So the ground state is nothing but taking the minus sign here. So we'll just replace the ground state by minus sign here. So this is the ground state. So how do we get the self-consistent equation? So we want to ask, when we modify the interaction or modify the order parameter, we want to adjust the energy, which is the minimum, right? So the gap equation satisfies when this differentiates with the gap, the order parameter. We want to set this is equals to 0. So from this equation, we will have 1/2 mu naught delta minus this part divided by 2 pi, and this differentiates with respect to the order parameter delta, which will give you cosine square k divided by delta square mu naught square, right? And then this is nothing but 2 mu naught square delta, right? So from this equation, we can get the gap equation. So that is what you learned from the superconductivity, if you remember. So this will work the same as the CDW of the parameter. So this one have cancelled out. So basically you get this term, square root of cosine square k plus delta square mu naught square. Okay. So, okay, at this point, you do some approximation first. Linearize at Fermi point, right? So that indicates, so you have this cosine k spectrum, right? You linearize it here, right? So it will somehow kf, so the spectrum will basically become k minus kf, right? And then you are in the integration, you can just replace for some window from minus lambda to lambda. So you can basically, you can, of course, you can directly integrate out this function, but for simplicity, we can just do this kind of integral in this region. So you get 1 equals to minus lambda near the Fermi point. So we still do the same thing. So near the Fermi point, we linearize the spectrum, so it will become k squared plus delta square mu square. And then this integral you know how to do, so that will give you the log function, right? So that's basically you get log 2 lambda divided by delta plus mu naught. Okay. So which you immediately get the gap function, which is something like this one. So you know for it is not 0 for any u naught, okay? And then as you know, okay, for any u naught. Now we want to say, but we still need to check one thing. So the spectrum, the spectrum is gap or gapless, depends on the energy, right? So we depends on the energy. So we need to compare this that equals 0 and this equals to 0, right? Which one has the low energy? And then if this one has the lower energy, then it must be gapped, right? If this one has the lower energy, then this will remain gapless. So we still need to consider this. So as you know, the energy in the mean field treatment is this one. We rewrite it again. Cosine square k plus delta square mu naught square. Okay. So as we replace this by this function, right? So we know this in terms of the linearized formalism. We get this is nothing but some logarithmic stuff, right? Which if this less than 1, right? This alpha greater than 0. So what I want to say is, what I want to say is we can find for some delta, this can be less than this one. Since this can be negative, right? So this part can be negative for some certain epsilon, delta. Right? So if this is negative, then the ground state will prefer to develop the CDW order. Okay. So which means it can be gapped. Okay. The idea can be negative, and it indicates the energy with CDW order will be preferred, which means CDW order is preferred.
老师问一下哦，
啊，
你可以到前几页写 Hamiltonian 的那个地方，就这个 Hamilton，这是什么 Hubbard model 还是？就这里不是有那个什么 normal order 吗？还是那个还是什么？那个叫做两个点点，那个叫做什么
normal order
是 normal order 啊。这个跟那个 Bostonization 那个 normal order 是应该是不太一样哦，一样的。
这个定义叫做 psi dagger psi 减掉 psi dagger psi
是这样
evaluate
是一样的定义。
所以这个会造成这一项等于零。
好。
Anyway, we basically conclude that we can find some finite order parameter such that the ground state is gapped because the CDW order has a lower energy, which is preferred. Okay, we can get a similar results, similar analysis for superconducting order parameter, which basically you can replace this by this by. Okay, so for the CDW order parameter, basically we choose this by 1/2 plus 1/2 minus 1I delta, right? This is our CW order parameter. And then superconducting order parameter, you can replace this one and then do the similar analysis, and then you will find the spectrum can be gapped. If it has low energy. However, from our analysis, mean field analysis, it seems that for arbitrary interaction, mu naught, u naught, you can develop the CW or the superconducting order parameter, right? So that indicates mean field seems suggest that interacting will always gap the system, which is not true because most of the 1D interacting system, they are described by Ladinger liquid, right? So, which means mean field does not get the correct result, which of course you won't expect mean field will give you correct results, right? So, which means we still need to learn RG to understand why the one-dimensional fermionic interacting system, the spectrum is gapless. So next time we show that RG analysis, the four fermion term, alpha goes to 0. Okay, so basically that's what we want to show you next time. Okay. So I guess I'm stopping right now. So if you have any question, you can ask right now.
我有个问题哦。
好。
就是我觉得，等一下我想一下，别人先问。 就是我的问题，我不知道这样问对不对，就是这边讲的 gapless 还是 gapted 的这个意义跟就是说没有 interaction 的时候，就是好像是很久学期初的时候是不是讲没有 interaction 的时候，那个意义是一样的嘛？因为我很好奇，因为我不知道是我听出来怎样，那是我说就是说像这种那个什么，不是你说的，是好像就是这样，就是像这种有 interaction 的，就是好像说，就是说你用那个什么，没有办法说像是那个什么 quadratic 那一种可以用一个那个 quantum number k，然后来描述。那如果说是这样子的话，那像这种是有 interaction 的，那可是我不知道，因为我们又说这个是 gapless 或 gapted 的，那我就觉得有点奇怪，说这边讲的这 gapless gapted 这个真的跟那个地方讲一样，就是说哦，这个是会导电的，不会导电，是这么简单吗？还是没有？
我不知道你想要讲什么，但是
对，
我理解的是说，你想要去理解 gap 跟 gapless 跟是不是可以用 k 去 label，跟是不是导电这三个的关联性是吗？
对，应该是这样子，对，
你想要问这三个关联性？好，这
因为
三个是完全没有，不是这三个。我先回答第一个问题，一个东西是不是可以用 k 去 label 它的话，是只有取决于这个东西是不是有 translational symmetry。
好，
这个东西如果有 translational symmetry 的话，我就可以用 k 去 label 它，因为 momentum 就是会是一个 good quantum number。
对，
那这个东西有 interacting 没有 interacting 都可以用 k label 它。如果没有 interacting 的话，我在任何 single particle level 下，我就可以用 k 去 label 它。如果有 interacting 的话，single particle k 是可以交换的，所以你没办法用 single particle 去 label。
对，我那时候好像问
Many
过，
particle 还是可以用 k 去 label 它。
嗯，
这是第一个问题。
嗯，
好，所以这个东西跟 gap 或不是 gap 没有关系，而是跟它 translation symmetry 有没有关系。好，那第二个问题就是说，这个东西是 gap 或者是 gapless，跟导电不导电有没有关系？这东西要分两个层次来去问它。首先，你导不导电是用什么方式去刻画的？因为导电不导电是可以用不同的方式去刻画的。一个是说是否在加偏压有电流，一个是代表说是否它的光学性质。比如说一个东西是金属的话，它就不透光嘛，对吧？就是那一个东西是就是说这个东西一个对应到的就是类似 transport， 一个东西比较对应到是一些local 的 measurement， 对吧？local measurement 就是说我只是看说这东西在transport 比较像是考虑电流的流动嘛。那流动不流动的话，这东西就是比较复杂一点啦。因为假设你有一个很小的 gap，但是你的平压加的比这个 gap 还大的话，你还是有办法去制造电流去流动它。所以这个方式你要说它是金属导电不导电，那就不是一个很精准的说法，对吧？因为你平压加的比它 gap 大的话，它还是会流，对吧？好，那我们再问一个问题，请问半导体它有没有电性？它也可以有电性，对吧？半导体还是有 gap，对吧？所以我们这个东西又要去理解，你要去怎么刻画它无形，是用对应到什么样的观测方法。那另外一个就是说，一东西没有 gap， 它有可能是不能导电的，对吧？假设这个东西是 many body 是一个 localized state， 它没办法流动东西，但是它可能没有 gap。它没有 gap 的意思是说，locally 的话，你如果去定义 density of state 的话，它看起来都是没有 gap 的，但是它有可能就不导电。
对，
所以这三个关系可以说是没有什么关联在比较精准的说法。
了解。